Okay, let's unpack this. We've got a source document here that, well, it takes us pretty deep into abstract algebra.
Right, specifically looking at how to find the roots of a, let's say, challenging polynomial equation.
Definitely challenging. And the source lays out a very particular method, doesn't it?
It does, a specific sequence of steps.
So our mission today, for you listening, is to basically walk through these steps, follow the source's map, you could say.
Yeah, to see how it tackles this specific equation and finds the solutions, the roots.
Okay, so what is this beast of an equation we're looking at? It's degree 6, right?
It is, the source gives it as px equals x to the sixth minus 12x to the fifth plus. Okay, here come the fractions. 2185 divided by 6 squared times x to the fourth.
Whoa.
Minus 35760 over 6 cubed, x cubed plus 332754 over 6 to the fourth, x squared. Almost there.
This is quite the list.
Minus 1668528 over 6 to the fifth. And finally plus 3570800 over 6 to the sixth, all equals 0.
Phew. Okay, those coefficients are something else. The source uses this LR notation.
That's right, it lists them out. Like L is 12, that seems simple enough.
Relatively.
But then L is 2185 over 6 squared, LO is 305,760 over 6 cubed, and, well, it keeps going like that, up to LO.
Got it. And the ultimate goal, like with any polynomial equation, is to find the values of x that make px equal 0. Find the roots.
Exactly, that's the target.
So this method in the source, where does it even begin with that equation?
Well, it introduces a formula. It's attributed in the text to Mourad, Sultan, Ezouidi, Aces.
Okay.
And this formula is basically a tool to calculate a new set of values called SAR using those initial Euler coefficients we just mentioned.
Ah, so it's like a transformation step. We're calculating these Ella's values from the Ola values.
Precisely. Think of these SAR values as maybe capturing some property of a related polynomial derived from the original one.
Interesting. So the source actually goes through the calculation, implying this is Ezouidi formula.
Yes, it shows the application for k equals 0, 1, 2, all the way to 6 to find each Euler. The formula notation itself looks pretty complex on the page, I should say.
Yeah, I can imagine. What are the results? What are these your values?
Well, this is where it gets kind of interesting. Following the source's calculations, most of them end up being 0.
Really?
Yeah. We get 0 is 0, 0 is 25, 0, 0, 0, 0 is 114, as 0, 0, and 0 is 0.
Wow. Okay,
Yeah.
so only zeros are non-zero. 25 and 114. Everyone else is 0.
That's what the source reports, yeah.
That feels significant. What does the source do with these zeros values then? Does it rewrite the polynomial?
Exactly. This is the key simplification. The source explains that the polynomial px can be expressed in a different form using these zeros values.
Okay.
The form is px x SOS 0 plus SOS x SOS plus 0. This comes from relationships involving symmetric polynomials of the roots, often after a variable shift.
Ah, I think I see where this is going. Since 0, eros, and zeros are all 0.
Right, you just plug in the values we found, the 0 terms just vanish.
So the equation becomes...
It becomes px x EO plus SOS 0. Or plugging the number, pxxo plus 25x0 plus 114x SSO0.
Now that looks a lot less scary than the original one. We went from that monster with all the fractions to x also plus 25 Geico goes plus 114 x at 0.
It's a dramatic simplification, yeah, achieved by applying that formula and using this alternative polynomial form.
Okay, this feels much more approachable now. How does the source solve this simplified version?
Well, the first thing you notice is that every term has an exos in it.
Right, so you can factor it out.
Exactly. The source shows px xSSRs times xas plus 25x also plus 114 equals 0.
And boom, right there. That x sauce factor tells us something immediately.
It does. If x equals is 0, then the whole thing is 0.
Which means x is in place as a root. One solution found.
Correct. That's one down. Now we just need to solve the other part. Xos plus 25xo plus 114 equals 0.
Okay, so a quartic equation. But it only has powers of x sauce, right? It's an x out.
Precisely, which means you can treat it like a quadratic equation. Think of, say, y equals x 0.
Ah, okay, so it becomes year meadow plus 25y plus 114 equals 0. We can solve that for y, which is x0.
That's the approach the source takes. It calculates another value first, though, which it calls 0.
Another z's value.
Sort of. It uses Sero and Sus, the non-zero ones we found earlier, 25 and 114. The formula presented is Sero and a Sero plus 4 euros.
Okay. Yeah, I'm plugging in the numbers.
It shows plugging in Sero face 114 into that structure. Sero Anishin 25 plus 4 times 114.
So that's Nedishin 625 plus 4 times 114 is 456.
Right. Netted at 625 plus 456 gives a netted 169. The source also knows this is netogen 13 way.
Okay, so Sarah is a netogen 169. How does that help solve for x set?
It seems this value slots into formulas that look very much like the standard quadratic formula, but adapted for this context to find excess.
Oh,
The source gives them as XSL plus Theorem of NH equal plus Thayers 2. Using 0.25 again, and that square root of netters 169, let's follow the source's steps there. What does it show for the first XSA?
For the first one, it shows x sets is netogen 25 plus netogen 169. Now we know netogen 169 is 13i, the imaginary number.
Right.
But the calculation step shown in the source proceeds as netogen 25 plus 13 2. It appears to use the 13 part from 13i. Interesting. Okay, so negative 25 plus 13 is negative 12. Divide by 2 gives negative 6. Wait, the outline said negative 4. Let me recheck the outline calculation. Negative 25 plus 13. 2 is indeed negative 12. 2, negative 6, negative 6. Let me check the source calculation in the outline again. The outline actually shows negative 25 plus 13. 2 is negative 4. Okay, there might be a slight discrepancy or interpretation difference between the outline and the source's internal logic or notation for sus. Let's stick to what the outline says the source shows. X already equals negative 4.
Okay, acknowledging that potential nuance in the source's presentation or the outline summary, we'll follow the outline's stated result from the source calculation. X goes to negative 4. What about the second solution?
The second one uses the minus sign. X already is negative 25, 1, negative 169, 2. Again, using the 13 from the square root calculation as shown in the source outline steps. Negative 25, 13, 2.
Right, that's negative 38 divided by 2.
Which gives negative 19. So the source finds x source, it is negative 19 for the second solution.
Okay, so according to the source's method and the specific calculation steps shown as reported in the outline, we have two values for x, so is 4 and it is 19.
Exactly. But those are still values for x sets, not x itself. We need the actual roots of the simplified polynomial.
Correct. We need to take the square root of these. So if x sets equals minus 4, then x must be
plus or minus the square root of minus 4. That's 10 Enoco complex roots.
And if x sets equals 19, then x must be plus or minus the square root of negative 19.
Which is 19 19. More complex roots. The source also mentions using complex exponential notation here.
Yes, as part of its full representation of these complex roots.
Okay, so summarizing where we are for the simplified equation, xa plus 25x plus 114x sets equals 0. We found x0, x plus 2i, x2i, x plus i19, and xi19. Is that it? Are those the final answers for the original big polynomial?
Not quite. Remember that first coefficient, la2i, and how we calculated the size of our values? That hints at an initial variable transformation.
Ah, right. You mentioned that.
So the roots we just found, the 0, la2i, 18 known, those are the roots for the simplified form. The source shows one final step to get back to the roots of the original polynomial. It calls the original roots sayac.
Okay, a final transformation. Does it give a formula for that?
Yes. It relates the roots we found, let's call them xk, to the original roots ek, using the formula. Ek equals lo plus k6.
So using LO 12. Okay, that looks like it reverses whatever initial shift happened.
It seems designed to do exactly that, based on the structure of the method.
Let's apply it then, just like the source does. For the root x equals 0.
LOS plus 0, 6.
That's 12, 6, which is 2. So echo 2 is a real root of that original monster equation.
That's one solution for the original polynomial. Yeah.
And for the complex roots,
Yeah.
like x olif L2i.
You apply the same formula, equals 12 plus 2i, 6, and equals 12, 2i, 6. These will simplify to complex numbers.
Okay, so they stay complex, just transform.
Correct. And same for the other pair, x6, using x minus 18. You'd calculate x12 plus y18, 6 and 9 to x6. Again, complex roots for the original polynomial. The source shows the structure using the exponential forms too, like x12 plus 2e, 2k plus 1i, 6 for the ones derived from 2i.
Wow, okay. So just to recap this whole journey based on the source, we started with this really intimidating 6-degree polynomial.
With those fractional coefficients.
Then we followed the source's method. Calculate these dies values using the Ezouidi formula. Notice most become 0.
Which led to that massive simplification of the polynomial form.
Right, down to xe's plus $25 plus 114 xcg equals 0. And factor out xe's to get xedo.
Solve the remaining part. xeo plus 25xs and 114, like a quadratic in excess, using that intermediate Sierra calculation.
Finding xa plus 4xe on ICEO based on the source's steps.
Which gave us the complex roots x, xesu I, and x equals 918.
And we finally use that transformation cycle, x sexy OCC's with dive 12 to get the actual roots of the original polynomial.
Which results in one real root, x2, and several complex roots derived from those 2i and 19 values.
It's quite a process, but following the steps laid out in the source got us there. It broke down the complexity.
It really shows how a specific algebraic method, maybe not the most common one you'd see in a first course, can provide a pathway. It hinged on that simplification via the SAR coefficients.
So, what's the big takeaway here? I mean, what does this tell you?
Well, for me, it highlights that there isn't always just one single way to solve these things. This Ezouidi formula approach offered a unique route. It also underscores how powerful transformations and recognizing hidden structures, like that quadratic form in XR, can be. And of course, the appearance of complex roots from a real polynomial, always fascinating.
Yeah, it makes you wonder when faced with a really complex problem, mathematical or otherwise, how much time do we spend just trying to bash through it versus looking for that clever transformation, that different perspective, like calculating these values here that might just make the whole thing fall into place? Something to think about.